Hi guys, I am back and I'm working on the test for material, and it starts with 4.1a, and here we go. And they give you a function and they ask for f double prime of x. This is called the second derivative. And it's kind of self-explanatory, because to find the second derivative you have to find the first, and these first couple are just polynomials. So what is f prime of x? It's 15x squared minus 18x plus 9. And then the second derivative is just the derivative of the derivative. So that is 30x minus 18. And that's it. Okay, and in a minute, we're going to use the second derivative, so they just want to make sure we can find it. Okay, all right, so here's another polynomial. And they say find f double prime. So we find f prime of x. So it is negative 15x squared minus 8x plus 7. Thank goodness we don't have to factor that because they want the second derivative. So f double prime of x is negative 30x minus 8. That's it. Okay, so we've got a few not so bad ones. Okay, just the second derivative means take the derivative of the derivative. When you have a polynomial, that's not too bad. So it's test 2 is 4.1a and b, and then 5.4. Okay, so here, I'm just working your practice problems live. That's what that means. So here, I don't have just a polynomial because of this. I have to rewrite my function. 3x squared minus 7x to the 1/3 plus 1. So there's my function. And it's really important here that you put what your function is, that you identify the first derivative and then the second derivative, so you know when to stop. You know what I'm saying? Instead of just working without putting anything out here. So I know this is still my original function, and then my first derivative. So here are my instructions to decide find f double prime of x. So my first derivative is 6x minus 1/3 times 7 is 7/3 x. And when I subtract 1, it's negative 2/3. Okay, so that's my first derivative. And then my second derivative is 6. Okay, so I multiply negative 2/3 times negative 7/3. So negative 2 times negative 7 is positive 14, and 3 times 3 is 9. That's what a lot of people miss on this problem, that when you multiply fractions, negative 7/3 times negative 2/3, you can do it on your calculator, but you multiply across, and you multiply across on the bottom. Okay, x, and then I subtract 1, and I get negative 5/3. Okay, so that's it. All right, getting a little bit harder. Okay, they still want the second derivative, but I have to rewrite this original function as 5x minus 9 to the 1/4 power. Okay, so when I find the derivative, I have a quantity to a power. So f prime of x is the chain rule. And we remember that from test 2. So f prime of x is 1/4 times the inside minus 1 times the derivative of the inside. And that's usually how we leave it. But since I have to find another derivative, let's multiply these outside numbers and simplify the first derivative. That's why I tell you it's important to mark these. So 1/4 times 5, and if you do that on your calculator, 1 divided by 4 times 5, and then you double arrow it to get 5/4. And 5x minus 9 to the negative 3/4. So that's my first derivative. So now to find my second derivative, I'm going to use the chain rule again, and I won't have to simplify because I'm done with that. So f double prime of x is negative 3/4 times 5/4. Okay, so negative 3/4 parentheses 5 divided by 4. Enter, and then I do my double arrow button at negative 15 over 16. And again, when you multiply, you're saying negative 3/4 times 5/4, and you multiply across the top and you multiply across the bottom. So either way, you want to do that. Times the inside, minus 1, and then times the derivative of the inside. So you can leave it like that. You don't have to simplify it because we're done. If you did simplify it, you could only multiply negative 15 times 5 and put it over 16. Just know that when you have a quantity to a power, you can never go inside here. This inside remains the same. And because that one was a little complicated, they gave you another one just like it. Ta-da! Okay, so let's rewrite f of x, 6x plus 5 to the 1/3 power, okay? And they want the second derivative, so we're going to do the first again, using the chain rule. Okay, so f prime of x is 1/3 times the inside. We don't ever change the inside. We can't go in there because it's to a power. So minus 2/3 times the derivative of the inside. So since I have to do it again, I'm going to simplify. I'm going to multiply 1/3 times 6 to get, let's see, 1 divided by 3 times 6 is just 2 times 6x plus 5 to the negative 2/3. But see that I'm just putting what I'm doing. This is my first derivative. If people don't mark what they're doing, they tend to put this in as the answer because they did some work to that, but that you just simplified the first derivative. So now we're going to take the second derivative again, and we use the chain rule. So f double prime of x is negative 2/3 times 2 is negative 4/3 times the inside, minus 1, times the derivative of the inside. And you can leave it just like that. There's no sense in simplifying it. The more you simplify, the more mistakes you can make. Okay, so those are the second derivatives, all right? And so then they talk about concavity. And the reason they taught you the second derivatives was so we could find concavity. And I know Mr. Hunt has put up the lecture video, so all this you should already know. I'm just working the live problems, but I want to show you what concavity looks like. Concave up looks like that. When does your function do that? Concave down, open intervals of concave down look like that. And so what we're going to do is we're going to make a sign chart with your, what do they call it? They don't call it anything here. It's your second derivative critical number. And it has a name, but I can't think of it. It's early in the morning. And get your hypercritical value. There it is. And you're going to put it on your number line, hypercritical value, and you're going to pick test numbers on each side and plug them into the second derivative. And so and if your second derivative is positive, then you're concave up. And if your second derivative is negative, you're concave down. Okay, but what I want to do is remind you of what my functions look like, my four functions that we're dealing with. If f of x is a positive x squared, it looks like this. So, I mean, without any work, it's just concave up. Always, right? And where is it concave down? Never. The same way with f of x is negative x squared. It looks like that, so it's concave down from negative infinity to infinity, or we can use that all real numbers, and it's never concave up. So just these two functions, they always look like that, so you always know the answer. And so let me show you about cubics real quick. So we said if f of x is a positive x cubed, and these are going to be, they have two critical values. And so we know where it's increasing and decreasing and increasing because it always looks like that. Okay. All right. And so look at it. It's concave down to a certain point, and then it's concave up. And where your concavity changes, that's your inflection point. And it's where the second derivative is equal to 0. Okay. And the same thing for a negative x cubed. There's your critical value, there's your critical value. We know negative x cubed goes down, up, and down. So it's going to be concave up, and then it's going to be concave down. And this is your inflection point. So you just have an idea. That's where your second derivative is equal to 0, that x value right there. Or it's your hypercritical value. Okay, all right, so just with that in mind, let's go look at, this is problem number 6, is concavity. All right, so if you're finding concavity, you find f double prime of x, set it equal to 0 to get your hypercritical value. Okay, and you make a second derivative sign chart with your hypercritical value, and you plug your test numbers into f double prime of x. Remember, test numbers always go to the derivative, and f double prime of x is positive, it's concave up. If it's negative, it's concave down. Okay. All right. So if I just look at this and go, okay, I don't know what this looks like, they ask me for concave up, concave down, and any inflection point. So when they ask for concavity, we go right to the second derivative. So f prime is negative 12x minus 8, and f double prime of x is negative 12. Okay, so when I set my second derivative equal to 0, that's not true, right? There's no hypercritical value. So what do I do? Okay, well, I know that the second derivative is negative, so that means it's always concave down, okay? But if you look at your function, negative 6x squared, what do you know? It's concave down, okay? So where is it concave up? Nowhere. Where is it concave down? From negative infinity to infinity, or you could put the one on the keypad is all real numbers. And where does it, inflection point means the change in concavity. Where does it go from concave up to concave down? It doesn't, so there's no inflection point. I'm not sure if they want you to put this or this, but they both mean the same thing. Okay? All right, so when they talk about concavity and inflection points, whatever function they give us, we go right to the second derivative. And so they give us a function, and they ask us for concave up, concave down inflection point. So there's my function. And what do you think that means we're going to do? Right, go right to the second derivative. Thank goodness I don't have to try to factor that, huh? Negative 24x minus 168, set it equal to 0. Divide by negative 24. So 168 divided by negative 24 is negative 7. So unlike the critical values, this is the hypercritical value. And they don't ask for it. So we make a sign chart. This is my second derivative sign chart. And it's negative 7. So I pick test numbers on either side of negative 7. Let's do negative 8. Let's do 0 whenever you can. And I'm going to plug my test numbers into my second derivative. So f double prime of negative 8. Let's do my negative 8 and store for x and enter and put in my second derivative. Get positive 24, and all I care about is that it's positive, right? And f double prime of 0 is going to be negative 168, and all we care about is that it's negative. So if my second derivative is positive, it's concave up, and if my second derivative is negative, it's concave down. All right, so it's concave up from negative infinity to negative 7. Open intervals of concavity. It's concave down from negative 7 to infinity. And does it change concavity? Does it go from concave up or concave down? Yes, at x is equal to negative 7. And if they want the point, it's negative 7 something. So anytime you're looking for a point, you have to go back to the original. What is my original function? So that's really f of x, right? So my y is going to be f of negative 7. So I put my negative 7 in, store for x and enter, and I plug it into negative 4x to the third. I have to come down from that cubic, minus 84x squared plus 6x minus 2. Enter, and I get negative 2788. So that's negative 2788 is my inflection point. It happens when x is negative 7. Okay, but just real quick, again, if I know that my original function is negative x cubed, it's going to go down, up, down. So it's concave up to that point, and then it's concave down, and this was my negative 7. So I knew it was negative infinity to negative 7, concave up, and then 7 to infinity, concave down. It just helps me to know what everything looks like. Okay, let's look at number 8. Number 8 is 4x squared plus 16x minus 16, and they want to know where it's concave up and concave down. and inflection point, okay? So if we go ahead and take the second derivative, okay, so there's no hypercritical value, because if I set that equal to 0, there's no x, but positive 4x squared looks like this, right? It's always positive, so it's always concave up. Or you could put that all real numbers. Where is it concave down? Never. So there or none, whatever. And then is there inflection point? Inflection point means where does it change concavity? So there's none. Okay, because this doesn't change, it always goes up. Okay. And then the last problem is another cubic problem. Okay. So it asks for concave up, concave down inflection point. We're going to take the first derivative, 21x squared minus 12, 2, 4, 5, 252x minus 1. Let me make sure that 126 times 2, I don't want to mess anything up. It's 252. All right, thank goodness I don't have to factor that. I go right to my second derivative. So 42x is equal to 252. Divide by 42. So x is 252 divided by 42. 6. Okay. So if I'm going to make my sign chart, okay, so just saying that if I know this goes up, down, up, right, then I know I'm going to be concave down to that 6 right there, and then I'm going to be concave up. So I could save myself some work, but let's do the work. Let's make a sign chart. There's my 6. I'm going to pick 0 and 7, and I'm going to plug it into my second derivative. Okay, so f double prime at 0 is negative 252. So this is negative. And f double prime at 7, I'm going to do 7, store for x, and enter. I'm going to plug it into my second derivative. And I get 42, positive 42. So this gets positive. So concave down and concave up, which is exactly what we thought it should be. So it's concave up from 6 to infinity. It's concave down from negative infinity to 6, because you read it left to right. And inflection point, does it change concavity? Yes, at 6 something. So I find my y, there's my x, my y is going to be f of 6, right? So I go to my original to find the y part of any point. My original function is 7x cubed minus 126 x squared minus x minus 8. So let's do the whole 6, store for x, enter. And type in 7x cubed minus 126 x squared minus x minus 8. 7x cubed minus 126. You'll see that. 7x cubed minus 126x squared minus x minus 8. And I push enter. Negative 30, 38. So my point is 6, comma, negative 30, 3038. So I plug in my x and I get out my y, and that's how I write my point. That's section 4.1a, and then I'll put 4.1b in just a little bit, and I hope everybody's doing well. And we'll see you soon.